Hey, hi friends. Good evening once again. Thanks for joining the session. In a series of the HR analytics sessions, we are trying to look at the applications of data science, machine learning in the space of HR domain. And we did discuss about various supervised learning algorithms which help us to do predictive analytics. So as part of this program, we are focusing on the supervised learning aspects of data mining concepts. So when we speak about data mining, or you can call it as machine learning, pardon my handwriting. Yeah. So when we talk about data mining or machine learning, it comes with different options. The training of machines can happen in different ways. Broadly, we are segregating them into unsupervised and supervised learning. Here, we'll only do descriptive analytics. If you remember this 4 stages that we talked about for analytics, we have descriptive, we have diagnostics, we have predictive, and we also have prescriptive analytics modules. And we are speaking about descriptive and diagnostic analytics, which are tightly coupled together in unsupervised learning techniques. But as part of this series of programs that we are doing, we are focusing only on supervised learning techniques. And here we will try to do predictions. Or you can call it as predictive analytics. Now, when you're trying to do predictions, we have a specific variable of interest. We'll represent that as Y. We call this as output. And we will have a bunch of input factors. Input or inputs, variables. Your data mining supervised predictive analytics models that we are talking about is all about identifying the cause and effect relationship between these two variables. I mean, when I said these two variables, we're speaking about output and input. So establish the relationship in such a way that you can explain this relationship on a mathematical equation. If you can do that, if you can do this, then you will be able to easily do the predictions also, given the input factors known. And when you're trying to do the predictions, we'll have to see whether this is numeric data that we are trying to predict or non-numeric data. We did look into this. Of course, we also have looked into this. As an example, we tried to predict the salary given the years of experience as a demonstration. And to do this salary prediction, which is a numeric data, we used something called as linear regression models. Linear regression model. And of course, we did some kind of a tuning variation within this model to build the model with more accuracy. Where the evaluation of the model is done using RMSE metric. This is a parameter, or this is a metric which is used to compare root mean square error. Okay, that's the full form. Where we take error, we square those errors, then calculate the average, and then the square root. This is probably, if you're familiar with the statistical calculations like standard deviation, then RMSE is like your standard deviation that we have to calculate. So this is about your numeric value predictions. Now we also have seen performance analysis in the form of logistic regression, where we try to see whether a defect circuit will be identified or not. Here we used logistic regression. So we are basically using the sigmoid curve, that is the S curve that we see in logistic regression, for analyzing the performance and streamlining the tasks. On the similar lines, we are going to look at some more scenarios. Of course, we also have done survival analytics. So as part of yesterday's session, we discussed the survival analytics concept, where we do a little more than what your predictions are about. So predictions is fine, where we'll try to identify whether the event will occur or not occur. But survival analytics is talking about duration analysis. So you're saying if an employee is going to resign, then we can use prediction methods saying that whether the employee will resign or not. But the duration analysis will also tell us when the employee might resign. The duration, right? After how many months. This basically allows the HR people to come up with an appropriate strategy to counter the decision of the employee to resign. Of course, we'll also have factor analysis being performed here. We'll try and understand which factor is influencing the event more compared to the other factors. This will also help us to address those appropriate factors and ensure that the employees are retained. Okay, this is something that we discussed. Now, today, I will be talking about one of the approach, which is considered to be one of the easiest approach in the entire machine learning fraternity, also known as lazy learner. This algorithm is also called as lazy learner. This is the other name given. In short, this is KNN model. We call it as classifier because in our example, we are going to use this model to do prediction on non-numeric data. So that means your output variable Y is non-numeric, and we'll try to predict that non-numeric value. But what is this KNN all about? As the name suggests, K nearest neighbors. Nearest neighbors. What does this nearest neighbors mean? Let me explain that given this diagram. So let's say I have data points like this, okay? Okay, let me erase this and let me put it here. But we have x-axis and here we have y-axis. X-axis, y-axis. Let's say this is A, this is B, this is C. So we have A, B, and C. So when you talk about this, right, let's assume that we have X and Y. So here we will have, assume X1, Y1, X2, Y2, X3, Y3. These are my 3 data points. I'm calling this as A, this is B, this is C, representation. So this data point is X1, Y1. This data point is X2, Y2. And this one is X3, Y3. Now, if you look at this diagram, right, a very simple 2-dimensional space where I'm putting X1, X2, right, these numbers, coordinates. When you look at these numbers and this diagram, basically, what can you say? Which of these three are similar to each other? Which of them have close relationships? It's a very easy answer, right? We don't need to think about much. A and B are related, or you can say A and B are more close to each other. So there are more similarities between them, right? These similarities can be identified from the distance. So how do we look at this distance? So A is x1, y1. This is y1. This is x1. This is B. You have y2. Here it is x2. And then here we have x3. And we have y3. The data points are farther, means there's a lot of deviation in them compared to the data points which are close to each other. So if you see x1 and x2 are close to each other, similarly y1 and y2 are close to each other compared to x1, x3 or x2, x3, y1, y3 or y2, y3. This diagram can clearly tell us that A and B are close to each other, right? Close means their characteristics will also be similar. Their overall characteristics will be similar because the data points are not that far away from each other, right? The data coordinates that we look at. So based on the data, we can say these have similar characteristics. Now we use this particular logic in order to do a prediction. It's a very simple logic. We use distance concept in order to come up with the similarities. And once we have identified the similarities, we will be able to do the prediction based on the most similar record. Look at this. Let's say this is handwritten numbers. Okay, you have handwritten numbers. This is number 1, this is number 2, number 3, number 4, so on and so forth. So in total, I have 0 to 9, 10 different numbers, right? Or you can say 10 different classes or categories. Okay, we are treating each number as a separate entry, right? I mean, separate value. So we don't look at 9 as high number, 0 as low number, and all that. We are just saying this is number, this is number. That's all. Identify that as a different number. Now, given this historical information, where a lot of people have different handwriting behaviors, so we are looking at people with different handwriting, handwritten numbers. Now, when a new number is given, or maybe when a new number is handwritten, we should be in a position to identify that particular number. So how is this done? Say, for example, I have this number. What do you think? What is this number? Is it 8? Is it 5? Is it 9? Or is it 4? So in order to identify this number, we are doing predictions, right? Given these numbers, we will have to identify which class does this belong to. So what I do is I'll compare these two. With each and every data point, I will compare this number. When I do the comparisons, of course, we're going to use the quantification techniques, that is the distance techniques, because lesser the distance, more the similarities. Okay, that's the logic that we'll have to consider. So we are going to measure all the distances, compare it, and then take the value which is the most similar. So if you look at this, the most similar data point is among all the data. So I found this most similar value, but this value is coming from a category called 4 or class called 4. This is a label given to that class, right? I mean, we are labeling it or naming it. Same way, because of these similarities, we are also identifying that this should belong to the same class, same category. Generally, what happens is in a team or in an organization, once the personal relationships are developed between two employees, they become very close friends. Generally, they plan their careers together. If you have two friends, they generally plan careers together. So if one person is resigning, then we will also be able to identify that the other person is also going to resign. Isn't it? So in order to build such a model, we use this distance-based logic to quantify the similarities. That's your KNN algorithm. For example, if you look at this data, assume, I mean, you can think about this as an employee resigned or not resigned. You can think about a person getting hike or not hike, or people working from home or not working from home, working from office. So binary examples I'm taking. Okay, and I'm taking two different factors, x-axis and y-axis. Probably you can say years of experience and salary are the two columns. Okay, so this is years of experience. This is maybe the age of the employee or the salary of the employee. Given these two conditions, will the employee get hike or not? Right, so we want to bring in that particular aspect here. So to do this, we are looking at, let's say, the data spread in the space. It's like just XY coordinates that we are having. We have just seen that ABC example, right? So same way, I have X, let's say X1 and X2 data. Here I will mark X1 data. Here I'll mark X2 data. And this is your Y, or you can say categorical data, output variable. Pink or blue class. All right? Now, if a new employee is given, what would be the scenario? Will that employee be given? When I say new employee, for the analysis, will I be able to identify whether the person is going to get bonus or not, right, or salary hike or not? That's the business requirement. So what we do is we just do a scatter diagram and bring in that new data. The square box is the new data. That's the representation. So as part of the prediction model here, the KNN process, we will try and see first on the distances. We calculate the distances so that we can identify the most similar record. In order to identify the similarity, we use this, okay, distance measure. And if you are familiar with the distance calculation, I will say x1 minus x2 whole square plus y1 minus y2 whole square. This is the standard equation, which is called as Euclidean distance. This is something that you probably have learned in your school days. We are talking about the magnitude distance, right? So this is x1, this is x2. What is this distance? From a magnitude perspective, right? So I'll take square because otherwise you will get negative values. And then we are also taking square root because we have squared. Same way here, y1, y2 is there. What is this distance? We are adding those magnitudes. That will be your total distance between the two data points. This is called as Euclidean distance. Next, we calculate all the distances for the historical data with the new data. And all those distances are recorded. Now, once the distances are recorded, we will arrange these distances in ascending order. Shortest first. And I will take the most closest or most similar record. In this case, it looks like the pink record. This is the most closest. So because it is so close to pink, we'll say that the characteristics of the new data, the square box, will also be pink class based characteristics. Right? Because of the similarities, because of the closeness with respect to the coordinates, we assume that it also behaves the same characteristics. Hence, we are labeling it as pink only. Now, this is based on one shortest value. So the k here that we are looking at in k and n is 1. So I'll say 1 and n. Right? 1 nearest neighbor. So we are taking only one shortest distance. But this one shortest distance could be a completely outlier. Right? Completely by chance something might happen. Okay, so to ensure that the distance-based algorithm that we are looking at is going to capture the pattern properly and not just distance, we take a different number of k altogether, right? We keep changing k to different numbers. Right? So if k is equals to 1, this is the case. If I take k equal to 2, then one is blue class, the other one is pink class. So what should I do in this case? So in these kind of cases, we look at among these two, which one is the closest. And I see pink is the closest here. So I'm going to assign the new record as pink record, pink observation. But there will be a scenario, right, where both the data points might be exactly at the same distance. So it is going to be an ambiguity case for your KNN algorithm in such scenarios, and it will do an arbitrary selection. One among the two categories is randomly selected, arbitrary. Now, to avoid these kind of arbitrary cases, arbitrary scenarios, we will use a k value which can never be equal to multiples of the number of categories that we have. In this example, I have a 2-class problem, pink and blue. So my k will not be equal to multiples of 2. Right? Number of categories here. Number of categories is 2, right? So we'll never have this value. In short, even number cannot be taken. You'll have to take odd number in this case. So when you take odd number, you'll never get ambiguity case. You'll always have a majority. And majority you can see is with blue, so we will stick to blue. For example, I'll draw in a small case. Okay, so let's say this is one group and this is another group. Okay, clusters, there's groups. There's a data point here. Now this is the center. This is the center of the records. When you measure the distance, you might feel that, or you might find that this is shorter. Right? If you take k equal to 1, right? If you consider k equal to 1, then you are going to declare that the new this record that we are looking at should belong to B, right? Category B. But when I take more k values, I probably see that there is more closeness here. So majority, will always have to go by majority. This will tell us that the A, B records that we are looking at, I mean the categories that we are looking at, right? They belong to this this cluster A or group A rather than the category B. When you take k equal to big numbers, so we keep keep on increasing the k value like this and ensure that we get majority always. But when you keep doing this, there is a challenge. For example, if I have 100 people, assume that I'm analyzing 100 employees, and I'm trying to identify what would be the case of a specific employee, whether the employee is going to resign or not. Assume this is my past data, historical data. I'm looking at 100 employees. Some of them have resigned, some of them have still working here in the organization. So let us assume we have 60 people still present, right, working, not resigned, whereas 40 people have resigned. This is your data set. Now what you do is you keep increasing the k value, which is nothing but measuring the distances. For a new employee, we are using k, which is equal to small n. Small n is nothing but 100 here. So I will have to measure the distance from the new record to all the existing 100 records. Okay. If this is the scenario, if n is equal, k is equals to n, if this is the case, then what will happen here? I will measure 100 distances, and among all the 100 distances, I'm going to take the shortest records, right? Shortest how many? 100 distance. But when I try to do this, always I will get the majority. What is majority here? Not resigned. Irrespective of who's the new employee, you are going to get the same result if you are working on this data set with k equal to 100. That is k equal to n. Right? So this is not going to work if you take a big number as well. Okay. So this is the k value here. On x-axis, we are trying to increase the k value. And we are seeing whether the appropriate accuracy can be achieved or not with respect to a given k value. When you keep increasing the k value like this, the accuracy might increase for the training data set. Right? But the same model, I mean, the same k may not work for a new data set, validation data set. I want to verify whether the k will work or not. And when we check, it might not work on the validation data set. So how can we expect that it is going to work on a new data set case if it is not working here? Right? So that is the challenge that we need to address here. So identify the K value, which is not too big, not too small, but the K value is giving us the result, which is appropriately higher and consistent for both training data and validation data. Only then we will have the confidence that it will also work on the new data. Okay, that consistency is important. All right, next. Just to ensure that you understand what we are doing here, there's a small example here. If you look at these data points, I have some ingredients, right? Something that we generally eat on regular basis. We have two factors with respect to these data points, and we also have the output data. It's a 3-class problem. We have fruit, protein, and vegetable. And we have these coordinates for each and every ingredient. Now, if I bring in a new data, this is historical data. We know what is food type also, but when you bring in a new ingredient altogether, it will be placed in somewhere in this particular spread. That if you mark those data points here, this is how the data points will be shown on the X and Y. But what we are trying to do is trying to identify similarities among the groups. And if I do that, if I try to group them, you'll see the dotted lines, right? And each of this group has specific characteristics. For example, fruits here are having high sweetness, whereas vegetables here have high crunchiness. X1 value is very high for fruits. X2 values are very high for vegetables. And both the values X1 and X2 are low for proteins. So this is the data that we are able to see. Now, if I bring in a new ingredient here, I'm not putting it in specific coordinates. This is just a representation. Now, what we're trying to do is we measure the distances with each and every data point here, right? And then based on the distances, we are going to choose where does this tomato fall. Now, to do the calculation, as we discussed, you will be using something called as Euclidean distance. Okay, we are going to use Euclidean distance. And this is your coordinates for the data points, tomato. Okay, so given this, let us try and look at the calculation here. So I have tomato 6 and 4, and these are my other data points, historical data points. Now, as soon as I get the new data point, the first things that we do is calculate the distances. So if I talk about apple and tomato, 10 minus 6 whole square, square root of 10 minus 6 whole square plus 9 minus 4 whole square. So this is 4 square 16. This is 5 square 25. Square root of 41. 6 6 are 36. So this is 6 point something. Similarly, we'll have to calculate the distance between. Okay, let me just mark this. 6.4. Similarly, I'll be having to mark the distance between lady's finger and tomato, which is 1 minus 6 square root of 1 minus 6 whole square plus 4 minus 4 whole square. So this is 5 square, 25, and this is 0. This is nothing but 5. So on and so forth, I will have to calculate the distances from all the data points here. And this is what you get. Now, what we do we have to arrange this in ascending order. So I'll say 5, 5.8, 6.1, 6.4, 6.7, and 7.6. These are the data points, ordered data points. Now, if I choose k equal to 1, then I will have to look at the shortest distance, single shortest distance. That is nothing but 5. But that 5 is the distance between lady's finger and tomato. And lady's finger belongs to vegetable. Hence, because of the similarities, we are assuming that the characteristics will be same, like here, lady's finger. Like for tomato, the characteristics are like lady's finger. So we'll have vegetable. Now, what if I choose k equal to 2? I will have to choose two shortest distances. But observe this, one is vegetable, the other one is protein. When k is equals to 1, there is obviously no question of majority, but here k equal to 2 is there. And in k equal to 2, one is vegetable, the other one is protein. So there is an ambiguity scenario, right? But in KNN, we'll first look at majority rule. If there is no proper case of majority, then we go for the shortest distance route. Right? Shortest distance. All right. So based on the shortest distance logic between these two, 5 is shortest, which is basically vegetable. Hence, we are saying k equal to 2 is also vegetable. If k equal to 3 is considered, then I'll also have to take this 6.1. So I'll have vegetable, vegetable, and protein. So I'll have 2 vegetables and 1 protein. Majority again, right? So k equal to 3 is not an issue. We have vegetable type. So you can see for different k values, we are getting the same result. It is basically saying it's a vegetable type. This is how we try and do the predictions. Now let us look into the sample use case. We'll look into a proper data and then we'll try to implement that in Python. So if you see here, we're loading a data set called ethnic diversity. And here we are also demonstrating, I am demonstrating how do you convert a data which is non-numeric to numeric form. So let me load the data set. This is the data set where I have 310 rows and 13 columns. So it's a table with 310 rows and 13 columns. When I say info, it gives us the information with respect to the result here. So we're looking at employee database. We have employee name, employee ID, position, state, zip code, gender, marital description, and all that, so on and so forth. Now, from the analytics perspective, if I have to try and look at the characteristic similarity, then employee name is not required. Right? From a characteristics perspective, employee name is not required. Similarly, employee ID is also not required to measure the similarities. These are just identities, right? So you can keep them aside. Then the zip code is also not required. Zip code is, though it is talking about number, it is a location that we have to see. So from a numeric standpoint, it really does not have any significance. So you can ignore that column also. Employee name, employee ID, and zip code. And we are trying to delete them from columns based. Axis equals to 1. So 13 values are there. All of them are gone, and we have only 10 values. So df is equals to df drop, and employee name, employee ID, and zip code, we have x equal to 1. This one is going to drop these unwanted columns, and that's exactly what we have. Now you can see your employee name, employee ID are not there, right? Out of 13 columns, only 12 columns are remaining. Next, the race column is something that we are going to look at. We are talking about ethnic diversity. So I'm going to see what are the various race that we have in our data set. We have Black or African American, white, Asian, ASEAN, American Indian, or Alaska Native, 2 or more other races. Hispanic is also there. So 1, 2, 3, 4, 5, 6 categories are there. Now, out of all these, how many times each category is repeated? We want to see that. And you can see white is majority, 193 cases. Okay, and we have the other cases also, but very less number of use cases are there. I mean, categories are there. Then we can also check data types. All of them are object type. Only the salary and age are numeric values, and remaining everything is object. In Python, object means non-numeric. Integer and float, these are numeric. Float is in decimals. Integer, you know, right? It is non-decimals. If you open the data set, you can see that this is non-numeric, this is non-numeric, right? All these are non-numeric except for the 2 columns, salaries and age. Now I'm going to use something called as label encoder, and this label encoder is changing the non-numeric data to numeric form. Let me show you. The position column that we are having here, we are trying to transform this position column. This is the designation, right? We're trying to change that non-numeric value to a numeric representation. So here we say transform and save it in the same column. Now, if I open the data set again, you can see the first column where you see position here are converted to numbers. Similarly, we can do it for state. Right? State is non-numeric, but here you can see numeric. Then we have the gender, marital description, right? All these variables that you see, we are trying to convert that into numeric representation. Now, if I again say D types, go back and do a D types, you can see all the data points are now in numeric nature, except for your output category, race. Given these details, we want to identify what is the race of the that particular employee. This can also help us to do the reverse engineering and see if there are any biased managers where they prefer a specific race or something like that. So that's where it can be used. Now I'm going to take all the columns. I have 10 columns, right? So it will be from 0 to 9. These are the column names. You can see from 0 to 9, we have column names. Except for the 9th column, everything else will be chosen as X. I'm doing that. N means, always remember, after colon, you'll get n minus 1 values considered in the range. So if I say 9 here, that means 9 minus 1, which is 8, is what we take. So that means 0 till 8. Whereas the last column, 9th column, is the output column race. So I'm going to define that as input and output. Then from sklearn model selection, we are importing train test split library. This library will ensure that the data can be partitioned into 2 different subsets. But I'm taking the the entire data set with respect to the 8 columns and the race column as well. So this has to be split into 80-20. This data set also has to be split into 80-20. So if I have 310 observations, out of 310, we want to split the data into training and test. So let us do that. So I will get 4 different data sets here: X-train, X-test, Y-test, Y-train. So 248 and 62. That is the breakup, 80-20% proportions. And then we have value underscore counts. We are again checking this, right? We are just checking that the training data and test data also give similar counts, and it should not be like influencing some category. The proportion wise, the data has to be similar to this entire data set, right? Whether it is a training data set or test data set, it has to be like similar. That's the reason why we are looking into the proportions. Then once we do the EDA, data preparation, and then data partitioning, in machine learning, we have already seen, all we need to do is import a specific library. So here from scalar neighbors, we are importing k neighbors class. Right, we imported that. And then we are saying k neighbors classifier. I want to do 3 distances, 3 shortest distances. N neighbors is equals to 3, means k equal to 3 is what you're setting. I'm defining this as KNN, and we are trying to fit that with training data. And using the training data, I want to measure the distances for each and every record in the test data set. You can see that we have 242 and 62 data points. So using 248 data points, we want to measure the distances for each and every record in the 62 test data set records. Right, and then select the top 3, the shortest 3 distances. Right, so that's the prediction here. I'll do the prediction. And once we do that, you can see the results. This is how it is predicting the results for all the 62 records, employees. But for these 62 employees, we already have the data, right? We already know the data, and these are the data. So we are going to compare these 2 values to understand how well the model has predicted. And to do that, I have again a formula, a function called accuracy underscore score. We are just printing the results with respect to Y-test and predicted results, actual comma predicted, and look at that. Very, 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 very low, not even 50%. And we also have something called as crosstab. This crosstab is going to generate a pivot table, for us, right? And this is stored in conf. So this is basically how we can, let's segregate the data and compare the results. This is 0. That basically is telling us that none of the details, American Indian or Alaskan Native, are correctly predicted. In the test data, we had 1 record specific to American Indian and Alaskan Native, and that was predicted as ASEAN. 1, 2, 5. So we have 5 ASEAN folks where 4 records were wrongly predicted for that. Only once the ASEAN is correctly identified as ASEAN person. Similarly, we have Black or African American. Again, the same thing. But you can see white is captured as white in majority of the cases. Right? White is identified as white. So the problem here is the accuracy is very, very poor, not even 50%. But when you do the same thing in the training data set, let us see what we get. 68% accurate, you can see that. And then you have good numbers on the diagonal. Right? So how do I improve this particular accuracy? Very simple. We will have to alter the K value and see at what K value we are getting good results. So to capture these multiple calculations, of course, you don't want to write multiple lines of code. So you're using loop function. We can use loops. First, I'm defining an empty list so that I will be able to capture the details that are being calculated here in the next continuous code. So I'm going to choose a for loop here. I say for I in range 1 to 50, range 1, 50, 1. This basically is going to allow us to come up with the K values from 1, 2, 3, so on and so forth till 49. Okay. So K value can be all these different options. So I'm going to pass this I here in a loop. So first it will take I is equals to 1, does the calculations, capture the metrics, then moves on to K equal to 2, it repeats, K equal to 3, it repeats. Right? So all added into ACC variable, and we are writing it in a loop code, for loop. The idea is to ensure that we check for different K value. All right. Now from from 1 to 49 records, right? So we'll have in total 49 records stored in ACC variable. Let's see that. 49 records are there, and these are the comparisons. 1, 0.38. This is definitely overfitting, right? So we'll probably have to identify where we are going to get good results. Again, if you look at these numbers, we will not be able to comment anything. So we will better visualize it to understand. So matplotlib, and then we say train accuracy. But this I'm plotting. So on the training data set, the accuracy is 1, then above 70, and then it came down. And after it came down, probably at observations number 8, 9, right? 7, 8, 9. That's where you see that the accuracies are falling down. Right? And after one point, it has become constant. This is with respect to training data set. Now, if I use test data set, then what happens? And you see, this is your test data set. We cannot choose K, which is very low, because in such case, test data set is very less, whereas train data set is very high. So this is definitely an overfitting case. Yeah, this is something like constant, so let's not worry about that. But I think, yeah, these records are better. Among all, this particular K value is good. So this is 10. Assume this is 10. So 11, 12, 13. K equal to 13 is good. Right? So K equal to 13 is going to give us the good result, is what your K-NN model will tell. When you try with different K values, this is what we obtain. So what you can do, you can come back to this, k equal to 30, you rebuild the model and check the accuracy. Look at that, it's definitely increased, 61.3. And on the training data set also, it is similar, 64.9. Okay, so this is how we use the lazy learner, which is a distance-based logic, to identify what should be the category for your new record for your predictions. So using historical data, we are trying to do the differences, that is the distance measures, and then we are getting this result. And using this, we are trying to conclude on the predictions. Remember, this is called as a lazy learner, and it is not trying to learn some pattern. It's just distance-based logic. So overall convergence, right, accuracy improvement and all that doesn't happen. Hence, it's called as a lazy learner. All right, friends. So this is one of the classification model that we have. One of the machine learning algorithm that we have, KNN. And right, we will probably discuss about a new algorithm, a new use case tomorrow. Until then, stay safe, be happy, and keep learning. Thank you all. Good evening and take care.